Okay. By the way, what would be the picture of it? How can I picture it? So at z equal to 0, you're going to have this point. Okay. At z equal to, for example, 1, so I'm just showing some cross section. You will have a circle actually, x square plus y square equal to 1, but this is attached to z equal to 1 actually. Remember? So this is a circle attached to z equal to x square plus y square attached to 1. And then I can attach, okay, no.
Three-dimensional.
Okay. So it's going to be a lot of so it's like take smaller circle and then take a bit bigger circle and take a bit bigger circle and take a bit bigger circle and put them on top of each other, so that's going to produce a really bowl actually. So that would look like something like that. Okay, something like that. Okay, but okay, this exists between z equal to 0 and 1. Question: what are the parameterization of it? So it's a clever one. There's no parameterization here. But if you think a bit carefully, you have a parameterization. So what's the parameterization of paraboloid actually?
जैसे सर t और कोई भी फंक्शन मिला होता है तो हम वेरिएबल t कंसीडर करते हैं.
So in other words, you have been given a function f of x y.
Yes.
Okay, so that's really f of x y. So you're going to use long patch actually, or a graph of the surface actually. So it's going to be uv is going to be uv and
u square
plus v square. So it would be f of puv. U square plus v square and k. What would be pu cross pv? I can have I, j and k for example. So the pu is 1, 0, 2u. Okay? And pv is 0, 1, 2 b. And it's going to be what? So this goes on. So minus 2u, minus 2b and 1.
Yes, sir.
That would be pu cross pv. So I need to do what? Integrate it. So what would be f dot pu cross pv? So the other two components would be 0, so it's going to be 1 times u square plus v square, so it would be simply u square plus v square. 0. Think about it. So it has 3 components, I, j, k, but I and j component are 0 here. The Lagrange dot products, those two will go away and the k's will be multiplied with k's, you're going to get this. And take it. So what would be the domain for it? What would be the domain for it? So u is really representing radius, so 0 to 1, and v is representing this angle, so it's going to be 0 to 2 pi. Just solve it. So you have that how much of f is flooding out to the surface. So we're going to compute it. Turns out to be theta by So in rest of the time, I'm gonna do the really last topic in this chapter. So what we did when we were, for example, dealing with that in our curve theory chapter actually. So we defined curves and how to find their lengths and how to integrate scalar field and vector fields over the curve. So what was the next thing that we did?
Green theorem.
Let's prove the Stokes theorem. It's a green theorem of 2 dimensions, green theorem in 3 dimensions. Stokes theorem. The next thing is to go through the Stokes theorem. Stokes theorem is valid for a surface. Before proving the theorem, I would like to make you think and carefully understand really the definition of a special kind of a surface, which is called a Stokes surface actually. For example, the green theorem was valid in green region. Stokes theorem would be valid. It's really the green theorem in 3 dimensions. So then, what was the green theorem? So if you have a 2-dimensional region and you take these micro circulations of a scalar field in that given region and sum them up, you're gonna get the entire micro circulation of the F along the entire boundary of the region. So we'll have something like similar. So I'd like to define a Stokes surface. Is everybody able to see this part? So obviously when you are talking about surface, we're going to talk about parameterization. Parameterization is something that links a domain U in 2 dimensions with something in 3 dimensions, right? Whose image becomes the surface actually. So imagine I have a 2-dimensional domain, so let's call this U. Okay? And imagine this is sitting inside a UV plane. I'm going to refer to this picture again and again. Okay? Now, let's assume that this region U, so it's an open region, so it doesn't include the boundary, for sure. Okay, so the entire theory that we have developed previously is defined on the open region side. So let's call this boundary as gamma. So I'm giving the boundary of U a name gamma. And when you include gamma to U, okay, so I'm giving this entire region. So U with boundary, I'm giving this name sigma. So the sigma is what? It's U union its boundary. Okay. And now I'm doing what? I'm mapping this entire region, including boundary, in 3 dimensions. So I'm here. X, Y, Z plane. So in X, Y, Z plane, I'm going to get what? I'm going to get some kind of surface. As I get something like that. So this interior region. So since P, you have to think of it. P is only defined on this inner part. It's not defined on boundary. Keep it. Second thing, So when you are having this inner part, you're going to get an inner part of this surface. So let's call this S.
Yes.
Let's call this S. And now let me define a map P tilde, or maybe P hat. That is not a map from, you know, U to S, but it's a map from sigma, okay, sigma to this region. Okay, so this is a surface, and to this surface, so it's also going to have a boundary actually. So let's call this boundary a curve C. Okay. Let's call this boundary a curve C. Okay. Now, currently you may assume that these both pictures are boundaryless. Okay? Because B is not defined on sigma. B is not defined on gamma. B is only defined inside U. So I want a map that takes this entire picture and throws it on this entire picture. So if it takes the point from within U, it behaves like P. And if it takes the points from the boundary, it throws them onto the boundary of this curve. Okay? So this is called extending the map actually. So I have this map P. So I'm extending this from sigma to this new, what do you call, region. So let's call it, say, S union C. Okay? S union C. Now if P bar operates onto a point UV, okay, so I'm calling that this extends P. So what do you mean by extension? So do you know the restriction and the extension of a function? Okay, so I hope you should know.
Yes, sir. Yes.
Okay, so it extends P. What do you mean by? So if you operate P bar onto a point UV, which is here, which is the domain of the P, it will give you the same output as.
Include the book.
Okay, so I'm defining P bar of UV as P of UV for UV inside the region. And if I take now a point, say UV, but from the boundary, okay, this is gamma, so it's going to give me a point on the boundary.
On a C curve.
So if UV, if UV
belongs to gamma
is a point in gamma, then I'm assuming that this PUV on the curve is here. Okay. So that's a bit machinery that I need actually. So I'm going to put this in words. Something that's precisely what. So from where we started, so we said I have a map P that is defined over an open set U, okay, and throws them on the set S, okay. And then I'm saying that let's extend this P, okay, and let's assume that the region, the boundary of this region is gamma and the boundary of this region is C. And let's extend this P to a new bar, P bar, okay, when it maps a point of the region U, it behaves like P, so it extends. So this shows that the P bar is extension, and what I'm doing is that if it takes a point from the gamma, it throws it onto the boundary of the surface actually. Okay, so it's kind of oriented surface. Okay? Let me put definition now. Because this is important, because this सवाल है ना, definition लिखना is like, you know, putting yourself in trouble. So what's a Stokes surface? So let F from R3 be oriented surface. And by oriented surface, that you can draw a normal vector actually on it actually. So you have inside and outside.
Yes.
Okay. So So it's an oriented surface. Parameterized by P. So the story that I told here, I'm going to write in words. From U onto S, U into R3. Okay. Let gamma is boundary of U and sigma is really U union its boundary, so it's nothing, it's U closure actually. Adding boundary into it. Okay? So U sigma U closure. So we're gonna say we say S is a Stokes surface. S is a Stokes surface if you can find such a map, you can find an extension. If number one, sigma is a green region. Okay, sigma is a green region. So this region is a green region with the boundary, and you can extend it because we know that the result that we have for the green region, you can take it to the Jordan regions and multiply connected regions as well. Okay. Our region, you can say, for which green theorem holds. Okay. So any region for which green theorem holds. Because I want this green theorem. Okay. And U is interior of it. Second is that there exists an extension of P on sigma. Okay, so we may call this extension P bar. ठीक है? Such that P extends a smooth map on a neighborhood, and the restriction of this map to sigma is 1 to 1. Okay. And P on sigma and roughly is 1 to 1. In other words, P bar takes the point from the boundary. For each point on the boundary, there is a bound there actually. No point is lost actually. So यहाँ boundary point कम और वहाँ ज़्यादा that thing is preserved. ठीक है? So you call such kind of, surfaces as the Stokes surfaces. ठीक है? ठीक है? Is it making sense? Good. Let's put a bit more. Maybe a remark here. If gamma is a closed curve in 2 dimensions, okay, it's a region where you can apply Green theorem. So it's enclosed the region where you can apply the Green theorem. So gamma is a curve. So if it is a curve, it must have some parameterization. So I'm gonna later in the proof I'm gonna denote gamma of t as the parameterization of the gamma. ठीक है? And I have another curve C there. I have another curve C there. Then what should be the parameterization of that curve? What should be the parameterization of that curve? How can I get that curve? Can you think of the parameterization of the curve C? And I know the gamma. So what do you think? T of gamma of t actually. More specifically P bar of gamma of t, because P bar is, really the extension of it, because P is not defined on gamma, so it's going to be P bar of the gamma of t actually. Okay. Later we will, denote this extension by again P as well actually. So I'm going to call that extension as P as well. Okay. So P of gamma of t, and I'm going to call this as a C of t. Okay. So C of t is, really P of gamma of t. So I'm just giving it a name. Like this has a gamma parameterization gamma of t, so this has a parameterization C of t actually. ठीक है. Are we happy with all this notation?
Yes.
So Stokes surface is what? Simple. So take a surface, or your ordinary definition. So you have U in R2 and you have S in the surface. So what you are doing in both, you are trying to put the boundary. So in U, I put a boundary. So now I have a U with boundary. Okay, so I included boundary and make it sigma. And then I'm saying that, okay, now this on new region, in which you have this region and boundary included, you are defining a new map P that takes this region with the boundary and maps it onto a region with the boundary actually. Okay, so now the surface also has a boundary. So Stokes surface is a kind of a surface which is oriented. Okay, it have inside and outside, and it has a boundary. That's a Stokes surface actually. Take it? समझ आ रही है बात? So I would like to do what for such kind of surfaces I would like to prove the Stokes theorem.
So ये प्रोसेस रिपीट कर बहुत कॉम्प्लिकेट करोगे.
नहीं, क्यों complicated? Too complicated. It's not that complicated. So I said I have a region U. So I have a region U, dotted region. U. It's an open set. And I mapped, I know that I have a parameterization, a good parameterization that can give me a surface here actually. Okay? So, but that surface does not necessarily have a boundary. And I'm saying that now let's put a boundary on U and map this entire region in U with boundary with a new map of P bar that is an extension of P, and as a result of this you're going to get a surface with boundary. Okay? So this surface is an interesting surface which has a boundary, which is a curve, and it is oriented, so you can draw the normal vectors, you can say which is inside, which is outside. So that's in the Stokes surface. Okay, in our previous definition, we never said that a surface can have boundary. Okay. So it's just simply the P of S, P of U. So S is P of U. So if there is no boundary here, how come an S can have boundary? Can't have a boundary. Okay. So now you are saying that let's put a boundary in it and let's put boundary in it, and then this kind of a surface is in a Stokes surface.
सर वैसे सर इन रीजन्स की हम वेक्टर फील्ड कंप्यूट करेंगे सर, इनमें बाउंड्रीज मतलब क्यों लाजमी है सर?
क्या मतलब वेक्टर फील्ड्स कंप्यूट करेंगे?
स्टोक्स थ्योरम सर आपने आगे रिलेशन बताया कि डबल इंटीग्रल.
Stokes green theorem was what? Green theorem was necessarily about the boundary actually. Think about it. So green theorem was necessarily about the boundary. So what does that theorem say? So he said that you have a two-dimensional region and you are taking all small circulations, computing the all small circulation of vector fields, the curl of the vector fields you are computing in this entire region, and sum them up. That entire, what do you call, sum of the curls within the region is going to be equal to the net curl of the f along the boundary. So it was all about boundary. So there was boundary actually. Okay, and now when I'm going to define an f, I'm going to define my f, for example, that is going to be defined not only on S but is also going to be defined on the boundary. And I'm going to say the same. Let's compute all circulations in the sphere and sum them up. This will be equal to the circulation of the sphere onto the boundary of the surface actually. That's what it's going to be. We have to justify. Okay. So previously the Green theorem mathematically was a good trick to turn a double integral into a line integral. You will see that here you can turn a surface integral to a double integral. That's what mathematically is going to. Okay. Why I got rid of the picture? Shouldn't have. Sorry. Shouldn't have got rid of the picture. Quickly redraw it. That's my U. This is gamma. The both is sigma. Okay. The gamma has parameterization, gamma of t. Hence, the gamma is parameterized by gamma of t, and then you have this p. So extension, I'm again denoting it by p. So I'm not putting p bar, so I'm just calling it p actually. So it takes this entire region and gives you a surface here, S that has a boundary c, and C has a parameterization C of t, but this is nothing P of gamma of t actually. This is the picture we're talking about. So we have a Stokes surface. So see, this is what you do in mathematics. When you have to say something interesting, intuitively this is a simple idea, but when you have to say it, you have to say it very carefully. Okay? So here's a theorem. Let S be a Stokes surface S be a Stokes surface. It's this kind of a surface. All thing is use all these notations. Okay. So it's a Stokes surface with boundary C, with parameter C, whatever you call it. Boundary C, and let F be a vector field defined on the neighborhood of S union C. Okay. Then this is really the conclusion. What is the conclusion? Then so it links the surface integral with the line integral. Then if you compute the all local curls onto the surface, so in other words you compute the surface integral of the curl of the vector field, this would be same as the flux of F along the curl. That's what we would like to show. His proof is bit work of patience. You have to stay with me. It's not difficult. It's not that difficult. Okay? Here's the thing. So let's just start with the one side of the equation. J.
सर जो सर हमारे पास रीजन है सर उसके जो रीजन के अंदर हम कर्ल फाइंड करें सर लोकल सर फिर उसको हम
Sum करते हैं।
उसको सम करें सर उस फिर हम कह रहे हैं कि सर जो बाउंड्री होगी सर उस रीजन की